Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing to look at carbohydrates. Last scribblecast lecture, we introduced carbohydrates and examined what the term carbohydrate meant. We looked at synonyms, sugar, monosaccharide, and defined the terms ketose and aldose. We learned that the number of carbons in the sugar determines whether you are a triose, tetrose, pentose. Hexose, for example, has 6 carbons in it and is a aldehyde-based sugar. If you say hexulose means a ketose sugar, a ketone-containing sugar. Now, in monosaccharides, the hexoses are by far the most abundant. Aldopentoses or pentoses are very important constituents in nucleic acids. Derivatives of trioses and pentoses are important intermediates in carbohydrate metabolism. What we want to do now is take a close examination at the stereochemistry of carbohydrates. Last scribblecast lecture, we learned that designation of stereochemistry using the RS nomenclature led to names that were too large and complicated, and hence DL nomenclature was retained. So we want to look at the stereochemistry of the sugars, stereochemistry of carbohydrates, and examine where this comes from. Now, all monosaccharides except dihydroxyacetone, this molecule, all carbohydrates have chiral centers except dihydroxyacetone, or as we named it last day, 1,3-dihydroxy-2-propanone. Now, all other carbohydrates contain at least one chiral center. The molecule glyceraldehyde has one chiral carbon and can exist in 2 enantiomeric forms. By convention, if the sugar has the same configuration as D-glyceraldehyde and the chiral carbon furthest from the carbonyl group is drawn as in the case of D-glyceraldehyde, then you have a D sugar. Now, in D-glyceraldehyde, the OH is drawn to the right when the carbonyl group is at the top. Therefore, if the chiral center furthest from the carbonyl group has the OH to the right, it is a D sugar. This is D-glyceraldehyde. So, let's say I have a glucose molecule. All right. So let's draw below this the glucose molecule. The glucose molecule has 4 chiral centers. Now we have OHs to the right and OHs to the left. What determines whether this is D or L? We localize the carbonyl at the top of the molecule as drawn in glyceraldehyde. When this is done, the chiral center furthest from the carbonyl determines whether the sugar is D. That is this chiral center. Okay. This chiral center right here determines whether you have a D sugar. And because it's to the right, this is D glucose. Now, the mirror image of D glucose is referred to as L glucose. So if I draw the reflection, and I didn't have to draw the C double bond O reverse because it's not chiral, but all the chiral centers are reversed. Because this is the mirror image of D-glucose, this is also a glucose molecule. The enantiomer is identical to its mirror image in every way except for how it interacts with other chiral molecules and how it interacts with plain polarized light, if you remember from last semester. So the mirror image of D-glucose is L-glucose. What makes you an L sugar? Look at the chiral center furthest from the carbonyl. It is to the left. And it has the same configuration as, of course, L-glyceraldehyde. Okay. I'll put CHO here, CH2OH, and an H. So this is L-glyceraldehyde. Hyphen aldehyde. Okay, so L-glyceraldehyde. All right. Now, the question is, how many stereoisomers do we get? You must remember that as we proceed in increasing the number of chiral centers, the number of potential stereoisomers you get increases. In glyceraldehyde, there is only one chiral center. When there is only one chiral center, there are two possible stereoisomers. If you remember, the formula was 2 to the n number of stereoisomers, where n is the number of chiral centers. So if we take a hexose, which has 4 chiral centers in it, and we get 2 to the 4th, and we solve that 2 times 2 times 2 times 2 times 2, 2 to the 4th gives me 16 stereoisomers. Wow. 16 stereoisomers. Now this is shown in a chart in your handout notes, and you can examine that chart. When you have 4 stereoisomers in the hexoses, 4 chiral centers in the hexoses, you get 16 stereoisomers, 8 of which will be D, and 8 mirror images. Now what's really nice about this, though, when learning the nomenclature, you do not have to learn the nomenclature of the L-glucose structures or the L-hexose structures. If you know the D sugars, all you have to do is draw the mirror image to generate the appropriate structure for the L sugar. And so hence you can learn the structure of the D sugars and know the structures of the L sugars. Well, you are responsible for all of the names of the structures you've had already in the handout notes. Glyceraldehydes, dihydroxyacetone. You also given problems with erythrose, threose, ribose, ribulose, mannose, glucose, galactose, fructose, and acetoheptulose. What we're going to do now is take a quick look at some of the sugars that you need to know. And of course, since you only have to draw the mirror image to get the L sugar, I'm going to focus on some of the D sugars. This list is not all of the sugars you will have to learn, but is a large number of the aldoses. So let's take a look And what I'm going to do is bring up the first one, if I can. Yes. So what we have here are the aldoses, the D-aldoses. Descending, we see increasing numbers of chiral centers. If we are looking at the D sugars only, when you have one chiral center, there's only one D sugar. I do not require you to know the optical rotation. I put it in there to indicate 2 points. First off, D and L have nothing to do with the way light's rotated. You see some of the D's rotate light to the right, they're positive, and some of the D's rotate light to the left, they're negative. So note that D and L nomenclature does not talk about optical rotation of the light, plane polarized light. It only details the structure, whether the OH furthest from the carbonyl, the OH on the chiral center furthest from the carbonyls to the right. So when you learn these names, you do not need to know the plus minuses. Okay. The first one, D-glyceraldehyde, of course its mirror image is L-glyceraldehyde. Each of these can have a mirror image. Notice when we get to 2 chiral centers of both OHs on the same side, you're an erythrose. If the OHs alternate, you're triose. Notice when we get to 3 chiral centers now, we have 4 D sugars named ribose, arabinose, xylose, and lixose. Ribose has all of the OHs on the same side. Notice that. All of the OHs are on the same side. If the OHs are staggered to different sides, well then you have xylose. If one OH is on the left, you're arabinose, and if 2 OHs are on the left, you're lixose. Okay. What about the hexoses? Well, if we have 3 chiral centers and there's 4 D sugars, you know when you get to 4 chiral centers, you're going to double that, and you're going to have 8 stereoisomers. Now, each of these has a corresponding L sugar. If I want to know what L-allose is, I just draw the perfect mirror image of D-allose. Notice allose has all the OHs for the chiral centers on the right when we draw the fissure. If the top one switches left and all the rest stay on the right, you're altrose. We've already seen the structure of glucose. Glucose has the second one to the left. If you memorize the patterns, it's easier to learn the names. If 2 are on the left and 2 are on the right, you're mannose. Okay. Gulose looks a lot like glucose and is often confused for glucose, so be careful. It is the 3rd chiral center that's on the left. And if the OHs alternate, left, right, you're D-aldose. Galactose is fairly easy to remember because the 2 middle chiral centers are opposite to the top and bottom chiral center. And so you just remember that pattern, it gets easier to remember. If the first 3 OHs are on the left, the bottom OH in the chiral center is on the right, it's talose. Notice it is these chiral centers that make you a D sugar. So, you're responsible for all these structures. And it's interesting that in the biosphere, D-hexose is probably the most prevalent and by far the most abundant monosaccharide sugars. Now we have some new terms to bring up. Interesting. And we'll do that right now. The first term I want to consider is the term epimer. What is epimer? Epimers are optical isomers that differ in the absolute configuration of only one of the chiral carbons. So I'm going to draw 3 sugars, and let's see if you can name them. Okay, here's one. I'll draw another. What kind of sugars are these? Classify them. Well, they're aldehydes, so they're aldoses. How many carbons in them? 6. So I am drawing hexoses or aldohexoses. You can use either term, although hexose is more commonly used. And so what sugars do we have here? Try naming them. What sugars? Well, the one on the left has the 2 OHs in the middle to the left. That is D, because the OH at the chiral center furthest from the C double bond O's to the right, this is D-galactose. What is the middle one? Well, all the OHs are on the right for the chiral centers except the second one, and in that case you have D-glucose. And the first 2 chiral centers are to the left, the second 2 are to the right, you have D-mannose. Okay, now let's reiterate. What is an epimer? Epimers are optical isomers that differ in the absolute configuration of only one chiral center. They differ in chirality at only one chiral center. Okay, so let's consider these. compare D-galactose and D-glucose. First off, are these two molecules enantiomers or diastereomers? Well, D-galactose and D-glucose are not mirror images, but they are non-superimposable. And they are stereoisomers, so they are diastereomers. What about D-galactose and D-mannose? Well, they also are diastereomers. In fact, all three molecules are diastereomers of each other. So why use the term epimer? An epimer is simply a special diastereomer. Epimers are diastereomers that only change, or only different in chirality at one chiral center. Let's look at D-galactose. This, and compare it to D-glucose. This chiral center, and that one's the same. This one and that one's the same. And the last one's the same. They only differ here, at that chiral center. Now, let's compare D-mannose and D-glucose. Well, at the second, third, and fourth chiral centers, they're identical. But at the first chiral center, they're different. So that makes D-glucose an epimer of D-mannose. D-glucose is also an epimer of D-galactose, because D-galactose and D-glucose only differ in chirality at only one chiral center. D-mannose differs from D-glucose in chirality at only one chiral center. But what is the relationship between D-galactose and D-mannose? Are they epimers? Well, if I compare D-galactose and D-mannose, I see I differ here, that chiral center, and I differ at this chiral center. There are two chiral centers different, that have different orientations between D-galactose and D-mannose. This violates the definition of epimers, and hence D-galactose and D-mannose are not epimers of each other. Remember, all epimers are diastereomers. All epimers are diastereomers. Okay. Well, what we want to do now is prepare to move on to an interesting finding in the chemistry of sugars. But to do that, we have to have some understanding of basic aldehyde chemistry. And often, this is the reason why carbohydrates are usually covered after you've covered aldehydes. So we're going to take a little short intermission and look at some basic chemistry that is observed in aldehydes. We can take a simple aldehyde, R, C double bond O, H. And if we react it in methanol, say, with some acid, it's very important that the acid is anhydrous, ANH equals anhydrous. So there's no water around. So we've just bubbled HCl gas through methanol, dry methanol. If we do this, we can get an OCH3 to attack the C double bond O. And an equilibrium establishes between a 1-methoxy alcohol the OCH3 of the methanol actually attacks the carbonyl. And we'll look at the mechanism in a second. Now, this functional group needs a name. And this name that we give for this functional group is a hemiacetal, because it's derived from an aldehyde. What's interesting is you could do the exact same chemistry on a ketone. If you did it on the ketone, and you don't have to use methanol, you could use ethanol or any alcohol group. You just change this methyl O group to an ethyl O group if you use ethanol. Let's use ethanol this time. So suppose I used ethanol here. And I used HCl anhydrous. Oops. So I have my OH. And this time I have an OCH2CH3. I now have, in this functional group, what is called, because it came from a ketone, it's called a hemiketal. Okay. The reaction can continue. If I hit it again HCl anhydrous. The OH gets protonated, forms a good leaving group, water leaves, and you end up putting a second methoxy. This is called an acetal. It's not hemi anymore. Likewise, if you take the ketone, hit it with ethanol, again, HCl anhydrous, you'll get RC OCH2 CH3 this case it came from a ketone, it's the full ketal. Now we're going to look at the mechanism of how these form, but before we do that, we really should identify how we can determine the name of the functional group. After all, how do you know something's an aldehyde? Well, you know something's an aldehyde because you look at the C double bond O. If it has an H off of it, you know it's an aldehyde. If it's a C double bond O with carbons on the other side, you know it's a ketone. How do we identify hemiacetals, acetals, hemiketals, ketals? Well, some simple rules. to be in the hemiacetal, acetal, hemiketal, ketal family, okay, what's the first thing? Well, I see to be one of those four, I must have single bonds to carbon and two oxygens singly bound to carbon. So I must have carbons and hydrogens attached to the central carbon atom. But that central carbon atom has two singly bonded oxygens. So two singly bonded oxygens. Now, what's the second rule? Well, what makes me hemi? Look carefully at both the hemiketals and hemiketal and compare that to the acetal and ketal. What do you see? You see an OH. If you have two singly bonded oxygens and one is an OH, you are hemi. And lastly, rule 3. How can I distinguish between the term ketal and acetal? Well, they're derived from ketone versus aldehyde. Aldehyde has an H. A ketone does not. So, just like aldehyde and ketone, if you have an H on the carbon, H attached to the carbon with the two oxygens, if you have an H attached with the carbon to H attached to the carbon that has the two oxygens, you're an acetal. If there is no H, you're ketal, if the two units are carbons. So you can use these simple rules to help identify whether or not you have a hemiacetal, acetal, ketal, or whatever. Now, this can be really tricky, and you can get very complicated structures. For example, I'll draw one right here in the middle and get you to apply the rules, and you tell me what I've drawn. So this guy looks quite complicated, but check rule 1. Find the carbon with the two oxygens. That's this carbon right here. This carbon has two oxygens singly bonded to it, and then it has a carbon and a carbon. Rule 2, is there an OH? One of the oxygens an OH? No, that means it's not hemi. Rule 3, is there an H attached to that carbon? That lack of an H. There is no H attached to the carbon, so it is not acetal. This would be a full ketal. Okay, so there you have it. Now, what I want to do is look at the full reaction mechanism as to how the hemiacetal and acetal forms. Now, the mechanism is identical for the ketal, no difference, and so we're just going to focus on the aldehyde mechanism. and try to explain why we need anhydrous HCl. So, let's take a look at the reaction mechanism. Again, we start with the aldehyde. There's two lone pairs here. And of course we're in acid, so whenever you're in acid there's lots of H plus around. So one of the first things that happens is we get an equilibrium attack with H plus, where we add H plus to the double bond O. Now, this is a resonance stabilized oxonium ion. It's in resonance with the carbocation. So if you like, this is a resonance stabilized carbocation. Now we know carbocations are susceptible to nucleophilic attack. So my nucleophile, of course, is methanol. So I can have methanol attack the carbocation that formed. Methanol has lone pairs here and here. And so it can come in and attack. If it does so, I get RCOH H. I have an OCH3. He still has his H. Don't pull the H off. When you give a mechanism, you must give the complete mechanism. You must show each step where the protons are lost, how they move. Now we have an equilibrium, and the H plus can come off the methanol. And it can be lost to the solvent. And you'll notice that this molecule is my hemiacetal. Okay, now the reaction can continue. I can add H plus again. You'll notice if I protonate the methanol, the OCH3, I'm just going back to this structure. So you can go backwards. This is an equilibrium. But alternatively, I could have a proton add to the OH. Now, just as in alcohol chemistry, OH is not a great leaving group, but if you protonate it, the protonated OH becomes a good leaving group because it generates a weak base, water. And so we can lose water. Water can depart. If we lose water, we get the carbocation. And note carbocation is resonance stabilized. I don't have room to draw it there. Okay, so let's draw it here. Okay. At this stage, another solvent molecule can attack, plus methanol. If it does, it goes there. You'll get this. And the final step, minus H plus, to generate or for acetal. So much for drawing straight lines. There we go. Okay, so there is the full reaction mechanism showing the conversion of the aldehyde through the hemiacetal to the acetal. Now, one question that arises is, why do we need anhydrous HCl? And I want you to examine this step. Notice the equilibrium that's taking place here involves the loss of water. Going backwards involves the addition of water. Hence, if there was water present, by Le Chatelier's principle, as you add more and more water, you would shift the equilibrium back to the hemiacetal, which would, in the presence of acid, drive it right back to the aldehyde. The absence of water helps drive this equilibrium right through to the acetal. Now, you notice for going backwards, both from the hemiacetal and from the full acetal, we have to add what? A proton. And what is a proton? A proton is acid. So if there are no protons around, the first step in going backwards, either from the hemiacetal or the acetal, is inhibited. Hence, we can reduce the concentration of H plus by making sure these products, when they are dissolved, are present in base. And hence, we say that hemiacetals and acetals are stable in base. So while it takes anhydrous HCl to produce these materials, once they're made, once we get concentrations, we quench the reaction, we isolate these materials, but if we're going to use them or keep them, we must have base to suppress the equilibrium. Otherwise, they will convert back to the aldehyde. Well, why did we bother looking at this chemistry? This is aldehyde chemistry, not carbohydrate chemistry. Well, let's take a close look at one of the most common carbohydrates, okay, glucose. So let's draw our fissure. All right. And let's ask a question. In the formation of hemiacetals, because this is an aldehyde, what two reagents did you need? You needed an aldehyde. Well, we've got that. And you needed an alcohol in acid. Well, we have alcohol groups. And although the fissure presents the molecule as a perfectly straight molecule, we know that these chains have bond angles of 109.5. They can wrap around. In other words, I could draw this molecule in a slightly different way. I could draw it and I'll just put in and you begin to see what might happen. I could draw the glucose molecule thusly. And you see, we have an aldehyde group, we have an alcohol, and we could envisage this guy attacking here. And if it did, that would produce an O minus. I get an H plus adding to this O minus here. He loses his H here. I'd get something that looks like this. And for clarity, I'll leave the H's out. It is a line formula. Now I'll draw this OH that forms from that carbonyl. It could be up or down. I'll draw it down. But I admit this could have been drawn up. That C double bond O becomes an OH when that oxygen links up. This becomes the sp cubed. This C right here is this carbon. What have I created? What kind of functional group? Well, this carbon has two singly bonded oxygens to it. Okay. It's a line formula, so we know there's an H here. H means it's in the aldehyde family. It's in the acetal family. There's an OH, so it's hemi. This is a hemiacetal. Okay, so glucose as a sugar has the potential of forming hemiacetals. It has a hydroxy. Why did I pick this OH to attack the carbonyl? What kind of ring did I make? Well, you made a six-membered ring. a cyclohexane with an oxygen in it. This cyclohexane with an oxygen, and what do you know about cyclohexane from last semester? Well, we know cyclohexane has perfect 109.5 degree bond angles, it staggers all the hydrogens. Cyclohexane is one of the most stable ring structures. A six-membered ring reduces ring strain. Hence, it is logical that the OH that would be used in making a hemiacetal would produce a ring structure that has lowest energy, strain, reduced strain. All right, is there any evidence whatsoever, that a sugar like D-glucose can actually do this? Well, in actual fact, there is. In solution, if we take D-glucose and we dissolve it in solution, we observe that in aqueous solution, glucose behaves as if it has 5 chiral centers, not 4. In the straight chain, we have 1, 2, 3, 4 chiral centers. But if we form the hemiacetal, these are the 4 originals, the hemiacetal produces a new chiral center. And so there is evidence that in solution, the hemiacetal is actually forming. Well, we're going to continue with this next Scribblecast lecture. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. Well, thank you very much.